Section 2.7 is called implicit differentiation. And the first thing I want to talk about is the two types of differentiation that we can do. The first type is the type that we've been doing. It's called explicit differentiation. Explicit differentiation is taking a derivative of y in terms of x when the equation can be written as y equals, with x all on the other side. So if you have the ability, and in fact all the problems we've done so far have already been given to us in this form, of having it written as y equals, then you're doing explicit differentiation. That's all we've done so far. Sometimes, however, it's either impractical, right? It's not helpful, it's not easy, or maybe even impossible to be able to write it as y equals. In that case, we're able to do something called implicit differentiation. So implicit differentiation is taking a derivative of y in terms of x when either the equation can't be simplified to y equals, or maybe it's just difficult or messy to do it that way. So in order to do this method, or to use this method, we have to treat both x and y as variables and use the derivative rules we've discussed. Okay, does everybody have that so far written down? Are you good, Noah? Not quite? It's okay. Okay, let's take a look at an example. This problem, we could solve it for y. All right? We could move the 37, we could divide by the x squared, and then we could square root. Everybody agree with that? Okay. Problem is that when we square root, then we would get a plus or a minus in there. And we'd actually have to separate the equation into two equations, the positive square root and the negative square root. We'd have to process through two different equations, and it'd be kind of messy to do. Not to mention that we'd have an ugly chain rule involved too, because we'd have a square root involved now as well. Okay? So I'm going to use this example, and I'm going to show you two ways of writing this. Normally, I wouldn't even show you one of them, but your book uses it, so if you want to use it, you can. I'm going to show you the one that I find to be a little bit more helpful also. Okay? All right, so the first one I'm going to use is I'm going to show you the one that your book uses, I guess. We'll do it that way. All right, so this right here has x squared times y squared, and it agreed? So we're treating this as though both x and y are variables, which means we have a product rule. So far, so good? There's a product rule there. All right, so when we do a product rule, we rewrite the first piece, x squared, and we take the derivative of y squared. Well, what's the derivative of y squared? 2y. Sounds like what we would have, except that it's not exactly 2y, because we're supposed to be finding the derivative with respect to x. So this is actually 2y, y prime. This is what your book does. So those of you who just said something different, just bear with me.
It's kind of like a chain rule.
It's a chain rule. It's exactly what it is. Because we know that there is a way that we can write this as y equals such and such. And even if there wasn't a closed form way of doing it, it still is y with variable x. So when I take the derivative normally, what's the derivative of y? Well, it's y prime. Right? And that's what you normally do. The derivative of y is y prime. So when we see the y squared in the problem, it's like having a chain rule. Well, the derivative of something squared is 2 times the something. But the derivative of this particular something, y, is y prime. So we get 2y and y prime as we're doing this piece of it. Okay. That's half of the product rule. The other half. What is the derivative of x squared?
2x.
2x. And I don't need to do x prime, because this is not a y equals. This isn't the function. I'm doing this with respect to x. Okay? Okay, and again, I'll show you another way of writing this so it'll make a little more sense of why the x prime doesn't show up, so to speak. And then I rewrite the other piece, y squared. Derivative of 37, 0 equals, and then the derivative of 4x, 4. So this right here is your derivative, all right? But we're actually supposed to find this when we're all said and done so that it says y prime equals. Okay? There's only a one y, in this particular one, there's only one y prime in the problem. So basically we're just going to do the same thing we would have done originally, but we're going to do it now. We're going to get everything else on the other side.
What happened to the 2xy squared?
This piece, the 2x, is the derivative of x squared.
Okay. Oh,
And then the y prime is the other part of the product rule, so we leave it as the same. This is a product rule,
okay.
and so I have two parts to the product rule. I have the original
Oh.
function rewritten, and then this is the derivative g prime of x. This is how we at least identified it before. This piece is the first derivative, or the derivative of the first piece, and this is the second piece rewritten. Does everybody see where all the pieces came from? It looks different when I do it in implicit form.
Yeah.
It definitely looks different. All right, the simplifying for this, let me remove all this red, hang on. The simplifying for this is going to involve writing this as 2x squared y prime. And I can actually, I'll do this piece first, I'll move this piece to the other side. So this is equal to 4 minus 2xy squared. I want y prime alone. Right now y prime is multiplied by 2x squared y, so what do I have to do? Divide by 2x squared y. So this is actually y prime equals. Now, if we can simplify, we do need to simplify. We can simplify a tiny bit here. What do you see that can be simplified? Yeah, everything's got a 2 in it, doesn't it? So I'm going to divide each term by 2. So I'm going to get 2 minus xy squared, over x squared y. I'd like for you to notice that your answer is written as y prime equals, but y prime equals something in terms of x and y on the right-hand side. Do you see that? I don't have just x's on the right-hand side. When I do implicit differentiation, that generally happens, is that the other side of the equation ends up with x's and y's in it. All right, the only thing that's different from what I just did in terms of how your book shows this and how I think is maybe a little bit more helpful to write it is that usually most books don't write this as y prime. The problem inherent with writing y prime is that the prime gets lost. It's just this tiny little piece. I mean, it's not a lot going on. Or it can be misinterpreted and somehow you think you wrote y to the 1 power or something like that. It's sort of an ambiguous notation. Most books will do this instead. They would write the 2, or the x squared, they would write the 2y, and in place of the y prime, they would write dy dx. It's a lot easier to lose a dy dx. No, I didn't say that right. It's a lot harder, there we go, to lose a dy dx than it is to lose the little prime notation on top of a y. So this is what you typically see a textbook do instead, just for that reason probably more than anything. Also, it becomes very clear that if you were doing a dy dx notation and you somehow wanted to take the derivative of x, writing dx dx is very obviously the value 1, right? Which is why we don't write x prime, because x prime is the same thing as dx dx, and dx dx would be 1. So it also becomes more clear that the fact that I don't really need a dx dx in the problem. So you've got that feature going on. So on the next one, I'm going to use the dy dx notation. I don't care which one you use. If you really like the y prime and you want to be careful to not lose the prime, that's fine. When I taught this last semester, I used the y prime the whole time. Students weren't too terribly thrown off or anything like that, but I do want you to recognize that there is that inherent possibility because of the notation. All right, so we're going to do a derivative. This says find the derivative of y prime of x implicitly. This is x plus 3 over y equals 4x plus y squared. Now there's lots of things you could do, so let me make one mention here. I'm not especially fond of the fact that there's a quotient here. I have to use a quotient rule, right? So one option is that I could multiply by the y on both sides, and then I don't have any quotient. What do you think? Sound good? I do this with fractions all the time with my like intermediate algebra class. If you can get rid of the fractions, they can usually handle the problem after that. It's the fractions that kind of make things messy. Well, here it is too. The fractions making things messy. So my first suggestion is actually for us to multiply this so that it says 4xy, which I know now I'm going to have a product rule. I mean, I get that. But I do end up having all the y's all on the other side, right? The y's are only on one side on this particular problem. It's not y equals, but at least they're all on the same side. So there's something at least a little bit cleaner about that. Okay, so far so good? Great. All right, so let's start with the easy side, the left side. What's the derivative of x plus 3? 1. So 1 equals. We'll do it here just to keep it clean. All right, now I've got 4xy, which is in fact a quotient, or is in fact a product, right? Right, I have 4x times y. So product rule says I'm going to write the first one, 4x, and I need the derivative of y. So what is the derivative of y? Y prime or dy dx. Okay, I'm going to use dy dx on this one since I used y prime on the last one, just to show you how it works out. It is not any different. So if you write y prime, you're going to get the same answer. And then the product rule says I use addition and I do my derivative in the other order. What's the derivative of 4x? 4. And then I rewrite the second piece, which is simply y. And I don't need dx dx because dx dx is 1. Okay? Plus y cubed. What's the derivative of y cubed? 3y squared. And that's exactly what I would do if it were just x cubed, but then I have to put in there dy dx, or y prime. It's a chain rule, just like the y squared was in the last problem. Okay? I've got the derivative of the cubing part, and then I have the derivative of y itself, which is y prime, dy dx. Now, the goal is to get the dy dx's collected sort of together. You notice there's two pieces of the problem on the right-hand side that have a dy dx in them, and there's one piece that doesn't. The one piece that doesn't needs to move because it's not like the other two. You know, one of these things is not like the other, one doesn't belong. The one that doesn't belong has got to go away. So we're going to move it to the other side. So I'm going to have 1 minus 4y on the left. And then what I end up happening on the right-hand side is that both pieces on the right-hand side have a dy dx, which means I can factor dy dx out of both of them. Okay, both of them have dy dx, so I'm going to factor the dy dx out. So if I take dy dx out of 4x dy dx, I have 4x. The 4y is not here anymore, I moved it. Then I took the dy dx out of the 3y squared dy dx, which leaves me with the 3y squared. Why in the world did I want to factor dy dx out? What was the purpose of that? Yeah, actually, I like the way you said that, Luke, and that's not even how I would have thought to say it. But to get it by itself, right? To get only one of them. I mean, that's really it. I need one of them on the right-hand side. Right now, I had two of them. If I factored out, I have only one of them now. And then I will be able to get it by itself by dividing the other piece to the other side. That's the goal. So I can in fact now divide the 4x plus 3y squared to the other side. So I end up with dy dx equals 1 minus 4y over 4x plus 3y squared. Now, I would like to say here real quick that if you chose to do this with the quotient rule originally, the answer ends up looking different. I'm just comparing this to what I have in my notes because I used a quotient rule when I did it in my notes. The answer looks different, but they will simplify to the same thing if you manipulate them. Okay? So if you choose to do the problem differently, for instance, than the book did, it might actually end up looking quite different in the back of the book. So if you need to ask a tutor in the Success Center, come ask me, is this the same answer? Did I make a mistake? Please do that, because that actually can happen on these particular problems, okay? Yes, Luke?
Do we cover how you have, like, the circumstances where you have to have dy over dx, so you can move, like, multiply the sides by dx? You know what I'm talking about? I just remember something about that a while ago, where you said it wasn't good to do y prime because you needed to.
We'll encounter that perspective of it when we get to antiderivatives, which is, I think, probably where you saw it before. Yeah, so hold tight to that thought. We'll get there. Yeah. All right. Let's do another one. Sine of xy equals x squared minus 3. All right, so what is the derivative of sine? Cosine. Now, it's not written here, but there's some understood parentheses going on, right? So this is a chain rule. Cosine of xy. I need the derivative of x times y, but x times y is a product, right? So I'm going to have to do a product rule to do that, right? It's okay. We've done product rule in both the last problems, so you know the product rule as it pertains to this. So I actually have got to have the x and the y as separate functions. So I'll write my x. What's the derivative of y? Y prime, or dy dx, plus. Now I need the derivative of x, which is 1 times y, right? Rewritten. So this is 1y, or just y. Equals, what is on the right-hand side? What is the derivative of x squared? 2x, and the derivative of the minus 3 is 0. So this is equal to 2x. All right, what I need to do next is this piece, this cosine of xy, is multiplied by both of those pieces that are inside the next set of parentheses. You guys see that? I mean, it's a multiplied in front. It's like factored out, sort of the way it's written. I need to distribute this through, and I know that feels maybe a little bit like it's being counterproductive. But the problem is right now the dy dx is embedded inside of a set of parentheses, and I need to get it out in order to solve for it. So you can do one of two things. You can either distribute it through, or you can do one other thing. Did you think of another option? You can divide both sides. Yep. Do you want to do it that way? To do the division? Okay, we'll do it that way. That's fine. So we can divide both sides then by the cosine of xy, no problem. That leaves me with x dy dx plus y, excuse me, equals 2x over the cosine of xy. What would I do next? Remember, the goal is to solve for dy dx. Yep, subtract the y. So this is going to be x dy dx equals 2x over the cosine of xy minus y. Then what? Divide by x. I'm going to write that a little differently just because I've got two pieces to what's going on the right hand. So I'm going to write it as multiplication by 1 over x. Because what I want you to remember is that when you do this over here, it applies to everything. So that each of those pieces over there is going to be multiplied by 1 over x or divided by x. So I end up with dy dx on the left. On the right-hand side, if I distribute this, and the reason I'm having to distribute is because I didn't distribute before. So, I mean, you still get to distribute at one point or another. If I take 2x over cosine xy and I multiply it by 1 over x, what's going to happen? Yeah, I canceled that x in that numerator. So this actually just becomes 2 over cosine xy. And then I have minus y over x. And again, this is only one way it could be written. In my notes, what I did is I actually distributed the cosine xy instead of divided by it. And the difference is that the answer here at the end is all pushed into one fraction. Like I had a common denominator and it combines the two pieces. That's not any simpler. It's just a different way of expressing the answer. Okay? Again, it's one of those things that if you look in the back of the book, if you approached it from a different perspective, it may not look quite the same when you're done, but that doesn't necessarily mean it's wrong. Are guys with me? Okay. Example number 4. Now, in your notes themselves, it says, find an equation of a tangent line at the given point. And then I have a line through with some additional directions. Do you guys see that in your notes? It's not on my screen right here, but you see that line through it? It's through that like that because in your homework, that's part of the directions of your homework, and I don't care that you do that piece of it. It's that the CAS is a computer algebra system, which is a calculator like the TI-89, or using something online that has the ability to work with the algebra and simplify it for you. So it actually has the ability to graph implicit curves. The graphing abilities and the calculators that you have don't have the ability to graph an implicit curve. So I'm not terribly concerned that you go find a computer that does that. You're welcome to do it if you'd like, but if you don't, that's fine too. Okay, so that's why that line's through it in your notes. However, the part that's still not got a line through it is the part that we're going to do. So we're going to find an equation of a tangent line at a given point. You guys ready? All right. So we've got an equation, x cosine y equals 1. Notice, and this is friendly, because they wouldn't have to give it to you this way, but the book always does. They give you both the x value and the y value that you're going to need in your equation. So we know y and we know x, which means that the only thing we have to find on this function then is m. How do I find the slope? The derivative, right? So I'm going to be finding a derivative, but I'm going to have to do it implicitly because I've got x equals the cosine of something. And on this one, while there's only one y, if I were to simplify this and solve it for y, I'd have to do something that would be an arc trig function, like cosine with a little -1. Do you guys remember that from trig? And at this point, you do not know a derivative for the inverse cosine function. You don't have one. We haven't discussed that yet, so it wouldn't even be possible at this point to do this problem differently. Okay? So we're going to do implicit differentiation. We have a product on the left, and we've got cosine of y, and y is itself a function on that piece as well, so we're going to have a chain rule over there as well when we do that. So first piece, x. I simply write it. What in the world is the derivative of cosine? Negative sign. So I'm going to put the negative in front of the x. I'm going to write down the sine of y. But then I have to take the derivative of y, and I would get dy dx. That is half of my product rule. The other half, take the derivative of x, and I get 1. And I rewrite the cosine of y. And then what happens on the right-hand side? It was secret. Yeah, equals 0, right? I could solve this for dy dx. I'm going to elect that I'm not going to. Not right now. I don't really care what dy dx is in general. I care what dy dx is at the x value of 2 and the y value of pi over 3. Do you guys see that? So I'm going to take this opportunity to plug those numbers in and then solve for dy dx. Do you have a question, Chance?
Where's the 0?
The derivative of 1.
Oh.
Yeah. So I'm going to take this spot as my place where I'm going to plug in my values for x and for y. So x is 2, y is pi thirds. I have dy dx here. So these are all multiplied. Plus the cosine, again, of pi over 3. And it equals 0. So all the pieces in red were the plugged in pieces. Now you have to remember something about a unit circle because you need some exact values here. Let's see what you remember. Do you remember what the sine and the cosine values are respectively at pi over 3? One of them is square root 3 over 2, and the other one is 1/2. Okay, and I don't write these in order. I'm just writing the two different values. One of them goes in one of the places and the other one goes in the other. Do you remember which one's which? 1/2 is which one, the cosine or the sine? It's cosine. And the square root 3/2 is the sine. So the way that I remember this is that pi/3 would be this value up here, right? Pi/6 would be down here. And they're switched x and y values, they just switch. This piece, clearly the y value is bigger than the x value, agreed? It's higher up. So the y value is the larger one. The larger of these two values is the square root of 3. So this value is 1/2 and square root of 3/2. Sine is y, cosine's x. So there's your little real quick trig review of the day. Grab a unit circle and just remember it. That's what you're going to want to do. I mean, if you just have it with you as you're working your problems, you're probably only going to have to work half a dozen problems that have this involved in it, and you're going to remember those details. It'll come back to you. Okay, and if it doesn't, then just sit down and take a little time and memorize it. It'll just be helpful to do that because you're going to see it happen
You said
on a regular
sine
basis.
is Sine of pi/3 is x value.
No, sine is the y value
Sine is the y. So why did you put in first value?
because this says sine of pi/3.
Right, and you had square root of pi/3/2 comma 1/2.
No, I didn't. I had 1/2 and then I had the square root of 3/2 like that. This is my y value. Yeah. All right, I need the dy dx to come back into my problem. Oops, that's a dy dy. That was a typo. Dy dx there. Sorry about that. All right, so I'm going to move the 1/2 to the other side. This -2 and this 2 will simplify. So this is actually negative square root of 3 dy dx equals 1/2. Right? Negative 1/2, yep. Sorry about that, thank you. And then I'm going to divide by the negative square root of 3, which is the same as multiplying by 1 over the square root of 3 with a negative. The signs are going to switch, which gives me that dy dx equals 1 over 2 square root of 3. And we are going to rationalize. I know you guys have asked me once before about rationalizing, and I said, no, we don't need to. Well, I said that because we were dealing with something that had an x underneath a radical. This doesn't have that. So we are going to simplify this. This is square root of 3. So this gives me square root of 3 over 2 times the 3 now, which is 6. My slope is square root of 3 over 6. Give me 2 seconds and we'll finish up this problem and then we'll stop, okay? Okay, maybe more than 2 seconds. The y value is pi/3. The slope that we just found was square root of 3 over 6. The x value is 2. I know you guys can simplify this, so I'm just going to cut to the chase and tell you this ends up giving you square root of 3 over 6x minus 2 square roots of 3 over 6. So let's write it as square root of 3 over 3. Did I get that right? And then plus my pi/3. If you want, you might also see the back of the book do something where it combines those two pieces. I can't get this written right, I'm sorry. Together and writes this as square root of 3 minus pi over 3. The reason that it looks like minus now is because you've got the negative in front, or they might write this as negative plus and this plus like that, which would be fine too. Either of those would be fine. So any of this over here would be an acceptable answer or a variation of an acceptable answer in that particular problem. Okay, we have 2 more examples.